Friends, we have now come to the last module in this series of lectures. First 8 lectures dealt with extraction processes for specific metals and also to start with some general principles of extraction and refining. We could have discussed a lot more, and if you refer to the books which are available on the subject, you get lot more details, many more details. But I have only selected the important metals and some of the important processes which are there in the industry, and discussed some important issues which are relevant from the points of view of production, and also some relevant issues which are important for understanding the theoretical basis of doing things the way we do. In this last module, module number 9, we will not discuss any specific metal as such. The entire module is devoted to issues related to energy and environment. Of course, now and then I will bring some reference to some particular extraction process, but many of the things I will discuss are of general importance, not only in metallurgical non-ferrous metal extraction, but maybe also of extraction of iron steel, maybe even other manufacturing process. The question you can ask is why I am going to discuss it in a course on non-ferrous metals production. Well, the answer should be obvious to you, because today no matter what you do, environment is a central issue, and perhaps you know the government has made it compulsory for every student, no matter what discipline is it, to be aware of the environmental issues, be it law, be it medicine, be it engineering, be it pure sciences. It is now a compulsory subject. Why is it a compulsory subject? Because environmental issues have become overriding. You cannot discuss anything ignoring environmental issues. As a matter of fact, there is now a new word called industrial metabolism. Not many people have heard about this word industrial metabolism, but you will begin to hear more and more of that as you grow older. See, by metabolism, human metabolism, what we mean is that body takes in food, takes in air. So, there is input to the human system in terms of materials and energy. Then they are processed in the body, and the body gains in terms of development of muscles, tissues, bones. So, there is a metabolism which depends on input from outside, and the system also rejects some wastes. Similarly, you can draw an analogy to any industrial system. The system runs because there are some inputs, the inputs in terms of materials, that includes water, energy, capital, labor, and the industry is sustained, it produces goods and services, but in that process it also rejects certain matter. Ideally, the industry should be a green industry. that nothing will be rejected as waste. Everything should be recirculated. If not recirculated, the waste should find useful application elsewhere. Actually, it is often said there is nothing which is a waste. Waste is only a raw material at the wrong place. Every waste can be a raw material for producing something else which is valuable. So, in a green industry, there will be no waste, and people are already talking about iron and steel industry, which one day would become a green industry, no waste whatsoever. We might actually, we are trying to mimic natural processes. You know, in natural processes, everything is recirculated. There are only two wastes in nature. I don't know how many of you are aware of that. These wastes are coal and petroleum. The coal comes out of millions of years of geothermal processes of plant matter that fall onto the ground, decompose, petrify, go under layers of soil. So, under pressure and heat, after millions of years, it goes through different stages of coalification, and ultimately it forms anthracite. You know, you have peat, then bituminous, subbituminous coal, etc., finally anthracite. Similarly, petroleum is supposed to have come from millions of years of geothermal processes of marine waste that were deposited in seashores, finally got submerged, and reactions took place over long times, produced petroleum. So, in natural processes, there was no way of recirculating coal and petroleum, but fortunately, they were benign wastes. I mean, those wastes caused no harm to anybody. They stayed under the sea, under the ground, out of our sight, out of our reach, at least in the initial stages, benign wastes causing no harm to anybody. Actually, much of our problem today has come out of trying to exploit those benign wastes, because we are taking out coal, we are taking out petroleum, we are burning them, we are processing them, then creating climate change, creating global warming, etc., etc., etc. So, those things that were benign wastes of nature have now come to haunt us. I should not digress from the main issue. The main issue is industrial processes ultimately should mimic natural processes, where things are recirculated. The CO2 that we exhale, or CO2 that came out of natural processes, at one time found sinks in two places. One is plant matter, vegetation. It absorbed lot of the CO2. About 30% CO2 went into the sea, because sea also needs CO2 for growth and sustenance of the marine organisms, be it algae, be it plants, be it animals, they all also need carbon. That came out of the CO2 which was absorbed from the atmosphere. Unfortunately, in the last 200 years or so, the industrialization processes that are based on combustion of fossil fuels, they are creating so much of CO2 that there is not enough plant vegetation on land or not enough capacity of sea to absorb that CO2. There is an excess CO2. That is what is causing today global warming, apart from also other gases like methane, nitrous oxide and some others. but CO2 is the main culprit, not because it is the most potent, actually CH4 is more potent weight for weight, but the sheer amount of CO2 being generated by modern industry is what is alarming. And that is why we must know what are the issues, and in these issues what role do industries play, what role does non-ferrous metal industry play. Even if it is not that substantive, it is our duty to see how things can be minimized. So, we will get into these issues and we will make some specific reference to non-ferrous metals production. Now, let us look at this slide. There have been some discussions on issues related to energy and environment earlier when we considered extraction of non-ferrous metals. Here, we will discuss the subject in more detail. What are the learning objectives in this module? They have been listed as follows. To understand the importance of energy and environment related cases in extraction processes, to understand the cost of development. I will explain this term cost of development. We talked about development, but development comes at a cost. To begin to live in a more prosperous manner, to become a more developed country, we have to lose out somewhere. Where we lose out, I would explain. The third point is to understand the scope of energy reduction in extraction processes. There must be scope, because there is always scope for reduction of energy consumption, but we want to know to what extent we can go. We have seen in the earlier lectures that if we recirculated scrap, then our energy consumption is less. That is one way of bringing down the energy consumption. But more important will be if we have an extraction process, how do we cut down on energy requirement, and then consequently the CO2 generation would also be decreased. Now, lastly, and this is very important, there are many terms we often use very loosely. We have to understand what are the exact meanings of these words. The words are waste, pollution, sustainable development, gross ecological product, life cycle analysis, end use analysis, subjective horizon, carbon footprint, carbon credit, etc., etc., etc. These are the terms which are becoming more frequently used in recent years, and I think every engineer, every metallurgist should be familiar with not only their meanings, but the context in which they have come and why they are important, why we should learn about the meanings of these terms. When we were students, I was an undergraduate student in IIT Kharagpur from 1962 to 1966. Now, at that time, we had never had discussions on energy, environment, quality, management principles, etc., etc. If at all they were mentioned, they were brushed off as soft subjects. Soft subjects which you pick up as you go along in life. You join an industry, when you work, you begin to understand the importance of energy, environment, quality, etc., etc., etc. So, by the word soft subject, it was meant that they were not very well defined and therefore not worthy of being taught in under formal education program, especially in undergraduate years. The emphasis was on hard subjects, hard not because it means difficult, hard means very well defined, like mathematics, thermodynamics, electrical engineering, physical metallurgy, very well defined. We know what are the things to be taught, we knew where to find the books where these were discussed, we knew what kind of laboratories should be run to explain the principles, we knew what to expect from the students at the end of the course, very well defined from beginning till the end. But nobody really knew about how to teach subjects related to energy and environment or quality, because those things were not very well defined in terms of content or scope. But things have changed now. I mentioned a little while ago, energy has become a compulsory, environment has become a compulsory subject. And once you make it a compulsory subject, you have to find out what is to be taught, what should be the scope, how it is to be taught, how do we bring in laboratories or examples to explain things. I remember my experience. I joined IIT Kharagpur as a teacher in 1980, and I was beginning to think that the importance of energy needs to be emphasized to the students, at least in the graduate level. So, I proposed a course at graduate level with the title Energy and the Metallurgical Industry. Initially, there was reluctance to accept that as an optional course, but subsequently over the years it has become a course which many people take, and it is considered to be a very desirable course because the subject has become so important. Now, it is fortunate that I had proposed that course, and in the process of teaching collected some materials, thought about it, talked to students, talked to colleagues, and finally, I have been able to write a book on the subject, to which I have referred to here earlier. It is called Energy in Minerals and Metallurgical Industry, authored by H. S. Ray, B. P. Singh and S. Bhattacharya. Now, that book came out of my concern for energy issues. Not so much I knew about environmental issues, but today, till today, there is no good book on the subject of environmental issues in process metallurgy. Many people are working. If you go to plants, if you go to R&D laboratories, people are working and doing a lot of good work on issues of environment. And there are many places where in the graduate level there is a course being given also, but still it has not become a well defined course at graduate or undergraduate level. I hope the view changes, and it will change sooner or later. Now, when I talked about a course on energy, I did not do the best job I should have done. So, later I realized that you cannot talk about energy and environment separately, they are very much related. And the environmental problems we are facing today come largely out of energy use. So, 80% of the environmental degradation problems are coming out of energy generation and energy production. Perhaps you know this, but again something on this I will discuss later. Actually, now people are talking about two things. We have to tackle the problem by first of all trying to see how we consume less energy, and then if we have ended up using energy, what do we do for remedial measures? How do we tackle the bad effects? Now, in the global context, the issues are combustion of fossil fuels, CO2 emission causing global warming and climate change. People are talking about alternate energy sources that will not depend on carbon. Now, here there is another word. People are saying we need decarbonization of the industries, means cut down on carbon consumption. They say we also need dematerialization. We need consumption of less materials, because if you consume less materials, you will produce less waste. So, you know that demilitarization is desired for world peace, but for world survival today, we need decarbonization and dematerialization, cut down on carbon consumption, cut down on materials consumption. We are talking from the global perspective. In the local context, environmental issues are related to energy use, which destroy the environment in and around industries. There are urban wastes, chemical wastes, there is problems with drinking water. So, there are all kinds of issues related to environmental degradation. What are the basic issues? The basic issues are the following. There are today serious environmental problems arising out of our industries. Non-ferrous metals industries have a significant role in countries' development and consequently environmental degradation as well. Policies and measures for environmental management are becoming more stringent, because the government is becoming more aware. There are also social groups which put pressure. At one time, people talked about end of pipe solution. What is end of pipe solution? End of pipe solution means let things happen, let them go through the pipe. At the end of the pipe, if there is a problem, we will try to solve it. So, the emphasis was on allowing things to happen, then tackle the issues that created problem when things have happened. That is called end of pipe solution, but end of pipe solution is no longer acceptable. That this is a wrong approach. Like that somebody says I will eat whatever I like, and if I have an indigestion, I will go to the doctor, he will cure me. This is an end of pipe solution. That is no longer acceptable. The ideal is not to eat things that can give you problem. You eat well, eat correctly, so that you do not have the need of a doctor at the end of the day. So, end of the pipe solution is when problems are generated by a process not changed in time or not changed adequately, and you have problems, you try to find technological solutions. There is now need to redesign product and the process to minimize waste generation at all stages. And by this waste, I mean gaseous waste, liquid wastes, solid wastes. Then environmental planning starts with awareness trainings, selection of right technology, product mix, and in-plant practice, long-term vision and commitment. So, if you do not want end pipe solution, then we need to do this, that we be more careful from the beginning. Prevention is better than cure. We are not talking about curing, we are talking about prevention of the environmental degradation problems as far as we can, and for that we need to have environmental planning right from the beginning, and to do that we have to select the right technology. We have to train people about environmental issues. We need to find out what product mix we should use, what kind of product we should produce which would have least impact on the environment, what kind of in-plant practice we will have, and we need a long-term vision, and we need a long-term vision and commitment. Long-term vision is another term for a longer subjective horizon. A subject horizon means to what distance somebody looks at. Let me give an example. Suppose you have a car and you find that the engine is not efficient, you are wasting a lot of fuel, and somebody says you buy this accessory which costs say 10,000 rupees, attached to the carburetor, your fuel combustion will be more efficient and you will be saving with the kind of running you are doing 500 rupees every month. But you have to put 10,000 rupees now to get that attachment to be connected to the carburetor. Now, there are two kinds of thinking in this. Some people will say 10,000 rupees, that is far too much, I cannot afford. This man does not have a long, his subjective horizon is short. Like if you go to those who are running commercial vehicles like buses or taxis, they go from day to day, they can't think of a long term vision. But see what this seller has mentioned. If you are saving 5,000 rupees, 500 rupees I mentioned, increase it a bit, say make it 5,000, 1,000 per month, or let us go back to 500 rupees, it is all right. 500 rupees a month means in 6 months it will be 3,000. In 1 year you are saving 6,000. In 2 years time you save more than what you had invested to start with, and after the 2 years you are at a profit of 500 rupees every month. Now, if you have a subjective horizon of 2 years, means if you can think up to that far, you will find this to be a very profitable proposition, that let me buy that gadget for 10,000 rupees, attach it to the carburetor. After 2 years we are not gaining, after 2 years we gain all the way. So, that is the idea of subjective horizon. This needs a long term vision. Many industries do not have it. And when you have a long term vision, along with must need a commitment, means it is not that you are committed on Monday and by Saturday you have forgotten about it. If you are committed today, you will be committed 6 months from now, you will be committed 6 years from now. That is the kind of management that is required today. Now, let me go through some definitions. As far back as 1946, there was a definition for the word waste. There are many more definitions, but I happen to have this paper with me and I have always liked this definition. It says, waste in its strict sense is non-use, spoilage, loss or destruction of either matter or energy that is usable by man and other living creatures. So, please note waste is not being defined in terms of non-use, is being used in terms of use. I will read it again. Waste in its strict sense is non-use, spoilage, loss or destruction of either matter or energy that is usable by man or other living creatures. So, what you are not using, but is usable, is waste. It is not non-usable. That is how Simons defined as far back as 1946, when people were just beginning to be aware of the issues concerning wastes. Now, if we talk about industrial waste in particular, there is waste, so called waste everywhere in this world. In industrial waste, we can define it as material or energy. Always think of waste both in terms of material as well as energy. It is not only material, please remember. So, industrial waste is material or energy discarded intentionally or unintentionally by industry during production of some useful products, regardless of whether the material is discarded to the atmosphere, to the land, to the waters of the earth, and regardless of whether or not the discarded material has any present or potential value or any effect on natural surroundings. So, it is a very comprehensive description that if an industry discards knowingly or unknowingly in the process of making useful products, it discards material or energy to the atmosphere, land or sea, regardless of whether it has any value at the moment or in future, that will be an industrial waste. Let us move now. Question is, why are we generating wastes? Most industries are generating wastes. Perhaps all industries are generating wastes, because it is part of industrial metabolism. And human being also discards things, solid as well as liquid. They need not be wastes. They also have a potential use, because if it goes for agriculture, into agricultural field, they become growth promoters, they become nutrients for the plant matter. So, they are really not wastes. But we waste, we generate wastes in industries which go nowhere. Some industries only dump whatever they are producing in the river at night, so that others cannot see, or in the sea, or they let into the atmosphere all kinds of gases, because they are not punished, or they cannot prove to be guilty. Maybe they do not know, sometimes they know, but still they do, because they think if they try to stop that, they will have to change the process, or if they want to bring in remedial measures, they will incur additional expenditure. Why are we generating wastes? Obviously, because we are digging into the earth's crust. All our industrial processes, especially metallurgical processes, we are getting essentially the first raw materials from the earth's crust. not only fossil fuels, but all the raw materials from metallurgical industry, which produces materials which go into other industries. So, let us go back to this earth again, with which I had started this course. Earth's radius of 6371 kilometer has half consisting of a core inside, presumably of an alloy of iron and nickel. Then there is an intermediate layer of 2870 kilometer thick, which is thought to consist of silicates of magnesium, iron, chromium, and also sulfides, tellurides and selenites. About this we do not know too much, but people have found by many studies to come to such a conclusion. The most important thing which is of our concern is the crust. We say the crust of about 30 kilometer thick is ordinarily accessible portion comprise, that is what we call crust, but normally we can access only about 3 kilometer level at the top, and this can be, samples can be taken out of this by deep boreholes. Some boreholes for petroleum have reached a depth of 600 meters, but generally we will say 3 to 4 kilometers is where we know what all things are available. So, when you talk about abundance of elements forming Earth's crust, we talk of only the top 10 kilometer or so of the crust, including the atmosphere, and this includes the atmosphere, mind you, because when we think of crust, do not forget oceans are part of that. Oceans are also on top of Earth, and the atmosphere also is part of the crust. Now, I had given long time ago in this series of lectures a table giving figures of relative abundances. Now, I am showing it in a form which is more friendly, viewer friendly. We are putting it in a logarithmic scale in terms of abundance. This is the abundance is logarithmic scale, and these are the elements plotted according to atomic number. Now, you know, out of all these elements, we have seen the very large number are actually non-metals. Non-metals are, first of all, we take out iron, take out halogens, they take out some elements which are not considered metals, because metals have certain features, but a large number of them are metals. Now, if you look at it, the highest percentage is oxygen, that includes the oxygen in the atmosphere also. Then comes silicon, then comes aluminum. You will find them all at the peak. Here is aluminum. You will find iron here. Then you find calcium, it will be somewhere there, calcium. Sodium is here, potassium, magnesium, hydrogen, titanium, chlorine, phosphorus. Now, very interestingly, it is not necessary that element which is very relatively more abundant is more common. I will emphasize it again and again, it is not so. It depends on utility value, it depends on how easy or how difficult it is to obtain from ores and minerals. So, we may say we see something is very abundant, but it does not make it more common. Like silicon is the second most abundant element, but you do not see silicon so commonly in everyday use. It does not have the right kind of properties. Silicon became very important when electronics came into human civilization. That is when silicon became very important. But in our everyday thing, silicon is not as important iron or aluminum. So, you understand that out of all these elements, we have discussed actually extraction of quite a few, maybe at least 25 or so elements out of these we have discussed. Others we have left out because maybe they are not so important or processes are very similar. Besides that, there was not enough time as well. But please remember, the 12 most abundant elements account for 99.5% by weight of the crust, and I have listed the 12 most abundant elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the 12 most. All other 86 elements together form 0.5%. Various geochemical factors have made distribution non-uniform. That is why we are able to produce some elements, although relative terms in the earth's crust they should not be so abundant, but somehow they have been segregated in some pockets here and there. And because that has happened, we are able to produce them. Had everything been distributed uniformly, it would be very difficult, like it happens in the case of seawater. In seawater, there is a uniform distribution, so it will be very difficult. But there are some places in seawater when there are concentrated sources. Sea nodules is one, some sea organisms are others which accumulate in them certain elements, say like iodine. Iodine was first found out from sea algae. So, fortunately, distribution is not uniform, but one or two generalizations we can make, which is very clear. Because oxygen and silicon are so very abundant, there will be a lot of silica, that is why you have sand everywhere, also clay, which is silicon oxide. Aluminum is also abundant, so we have lots of aluminum, mostly as aluminum silicate, clay, we have bauxite, we have various aluminum ores. So, these three are abundant. Now, till 200 years ago, nobody thought of much use of aluminum. Aluminum was not a metal which was produced in large quantities. It could not be produced in large quantities because there was no electricity, there was no Bayer's process before the middle of 19th century. But today we cannot think of a world without aluminum. Silicon we still have not found widespread use in our everyday life, but aluminum we have found. Interestingly, the metal with which we are most familiar, iron, it is only 4.7% in Earth's crust, but still our age is based on iron, for two reasons. Firstly, the properties that we get from steel, and also we have deposits which are rich in iron, and it is relatively easy to extract iron from iron ore. Okay. Now, our extraction processes are improving, but still there are some lower limits of grades from which commercially we can extract things. The poorer the grade becomes, more complicated the process becomes, there will be more rejects, more environmental problems. Now, here I have given some tentative figures about the lower limits of workable grade of deposits. I put aluminum as 35, although mostly we do at much higher grades. Iron 30 I have said for carbonate ore, for oxide ores 55, 60, maybe 50, that should be the minimum. Manganese 25, chromium 25, zinc 5, lead 4, nickel 1.5, copper 1.0. Some people think for nickel it can go down to 1. We have newer techniques. Copper 1.0, because we have a flotation process which will take it to 125 or more in one step. Of course, we know that silver, gold, platinum deposits are of very low concentrations, until we have processes for extraction of these precious metals from poor grade ores. Now, coming back to the environmental problems that come in metallurgical industries, here is a comparison of hazardous wastes that is produced in different industries. This is hazardous waste, means something which is not benign waste. It is not a waste will cause no harm to anybody. These are wastes which are harmful. Here is a scale in terms of liters production per employee per year. We have taken a strange kind of parameter. Foods and beverages, textiles, they all produce hazardous wastes. Then we have here, I will have to find out what this is. Wood products, paper, printing. You see, chemicals, petroleum and coal industries produce a lot of hazardous waste. Non-metallic products also produce. Basic metal products is where maximum hazardous wastes are produced. Basic metal products. Then we have fabricated metals, transport equipment, other machinery. So, the metal industries or industries connected with metal produce a lot of waste, good amount of it hazardous waste. So, there is tremendous importance of environmental issues in relation to metal industries. We can no longer ignore them. If you talk about non-ferrous metal industry in particular, this industry also generates a lot of waste. The worst offender is aluminum industry, where 2 tons of red mud is produced for each ton of aluminum produced. Imagine the magnitude of the problem. You have bauxite which is leached in Bayer's process by sodium hydroxide. Aluminum, rather Al2O3 is dissolved as sodium aluminate, but things that are there in bauxite and that are not dissolved go into the undissolved part and forms what we call red mud. The color is red because of iron. It would also have titanium. It would have some undissolved alumina, and its volume would be huge, 2 tons of red mud for each ton of aluminum production. If in our country we produce 300 tons of titanium, 300,000 tons of titanium will produce 600,000 tons of red mud. Where are we going to keep this red mud? In open fields, of course. We do not have a desert everywhere. Where you put this red mud, that land is not available for anything else anymore. And not only that, because red mud has come out of an alkali leaching process, it contains alkalis. Not a very happy situation when alkalis come out of that red mud dumps and go in the surrounding areas. And as of today, till today, we do not find a bulk utilization of red mud. A bit of here from here, a bit of there can be done. What do you do with all that red mud? The other thing is connected with power generation. It is not peculiar to non-ferrous metal industry. Whenever we are depending on thermal power, we are burning coal. When you burn coal, the ash is left behind, fly ash. Why we call it fly ash? Because it is in such a fine form, it flies everywhere. There is also we call something called bottom ash, which comes out of the reactors at the bottom. It is coarse coal, it does not fly. See how much a fly ash will be used. Over the years, the grade of coal that we were mining has become poorer and poorer in our country. When we were students, 22% ash coal were found. Today, it has generally gone to 35-40% ash. So, now many industries talk about importing coal from elsewhere where the ash content is less. When you have high ash content coal, we can wash them, we can try to wash away the ash part, but still everything cannot be removed. There is no beneficiation process to separate the carbonaceous matter and the non-carbonaceous matter ash, because they are very strongly bound together. At best we can go down to 18 or 20% ash. Suppose a coal has 20% ash. So, if you burn 1 ton of coal, 0.2 of that is coming out as fly ash. It flies into the air, it goes all in the surroundings, it covers the fields, it covers the rivers, it covers everything. And if you are careful to take it out at a certain manner, you have to put it at one place. What do you do with this coal ash? Fortunately, some uses have been found for coal ash, because coal ash is now going for making embankments. People are trying to use coal ash, from coal ash trying to make building materials. They are trying to put coal ash, fly ash in the fields, agriculture fields, to increase porosity. That at least in the short term helps vegetation. But we forget about one waste, and that is the CO2 which is going out in the atmosphere. That is an important waste. We are not doing anything about it. We will see what we can do. Now, do not say it is not a non-ferrous metal production problem, because all non-ferrous metal industries that are using power from thermal power plants are also contributing to this problem, fly ash generation. Red mud, vanadium sludge, waste cathode from carbon from the aluminum smelter, the waste from the ilmenite processing industry, etc., etc. There are many where you have the waste being generated. And there is always a gap between technologies of production and those of pollution abatement. I will stop here and just explain why there is a gap. Technologies of production go on improving, because all industries want to produce more, but they are not worried so much about the pollution problems, because so far there was not enough pressure on them. There were no incentives to develop technologies for pollution abatement. There were incentives for improving production methods, because that gave them large production, they cut down on cost, the things became more efficient. So, the gap between technologies of production and technologies of pollution abatement have widened over the years. It is only now because of pressure from the government, from the scientists, from the public, that all industries have to think very seriously about pollution abatement. I will come to this, and I will start with this once again during the next lecture. Thank you.